Hey guys, here we are for chapter 6. We're going to talk about populations. Today for chapter 6.1, it is about populations change in size. Your essential question today, how are population sizes relegated in nature? Or in other words, how does nature keep populations in check? Now let's dive in, take a look, and see what we have. First off, what is a population? What are we talking about when we use the word population? Textbook definition: group of organisms of the same species live in the same geographical area and interbreed. Nothing wrong with that definition, it's just hard for me to remember. My personal definition: same species, same place, same time. They have to be able to interbreed, but that little 3-term helps me work out, is it a population or not? Or are we talking about something different? A population is a reproductive group. Organisms tend to breed with members of their own population. Once again, I've talked about like grasshoppers out in my field. Well, the grasshoppers out in my field tend to breed with other grasshoppers in my field, as opposed to flying to Canvas to breed and then coming back to my field. People in Gainesville tend to breed with people in Gainesville. We talk about having sex. People here tend to have sex with people here. People over there tend to have sex with people there. We talk about different populations. Same place, same species, same time. Now the word population refers to the group in general, but we also use it to talk about size. We may say, what is the population of Gainesville? We mean how many people are here. But we tend to mean how many people are here now, as opposed to what was the population in Gainesville in 1920. It could be a different number. So it's referring to same species, same place, same time, group of organisms. I can talk about a population of mice, population of deer, population of humans, and I can also use it to talk about the number. What is the population in the forest? Talking about a particular organism. Then we'll also talk about density and dispersion. Density and dispersion. Density, the number of the organisms in a given area. Number of individuals, same species in a particular area. And in this, a lot of times we talk about it like per square kilometer or something. How many organisms per square kilometer for our density. The more animals per square kilometer, the higher its density. The fewer animals per square kilometer, the lower its density. Gainesville is less dense than New York or Miami. And we can talk about dispersion, where we find them, the pattern of distribution of organisms. And we typically use 3 different terms here. We talk about them being even, clumped, or random. Like trees in the forest might be fairly evenly spaced. Dandelions in a field might be clumped because they tend to drop their seeds and get a whole bunch in this area, not as many in that area. And it can simply be random. About rattlesnakes in the desert. These are sort of solitary organisms, so they tend to be randomly distributed, as opposed to deer, who tend to be clumped because they're social animals. Anyway, even, clumped, or random. Now size, density, dispersion, and some other properties can be used to describe populations and also used to predict what's happening within one. And we just want to talk about in general, how does a population grow? How does it go from being small to big, big to small, what have you? Now a very simple formula, if you will, is basically just going to be births minus deaths. Whatever our population is, plus the births minus the deaths, lets us know what our population is. So it'll change over time. Now, obviously, if we're talking about growth rate, I talk about how many people are in Gainesville today, or this year. We started with this many were born, this many were died. I add, subtract, and I have population at the end of a year. Now, one thing that we're not talking about here is immigration and emigration. Immigration is when people move into a town, city, or country, and emigration, spelled with an E, is when they move out. So normally we have to talk about this as well, because it's not unusual for organisms to leave an area or other organisms to come into it. But anyway, births minus deaths, and then we take in who's moving in and who's moving out, That gives us our population. And a growth rate, expression of the increase in the size of an organism over a period of time. Normally we're talking about a growth rate. We do sort of look at a period of time. What is the growth rate this year? What happened over a decade? Now, over time, growth rates of populations change because birth rates, death rates either increase or decrease based on environmental conditions. What's happening? Is it ideal or not ideal? But anyway, growth rates can obviously be positive. The population's growing. They can be negative, and it could be zero if the population stays exactly the same. For the growth rate to be zero, though, the average number of births must equal the average number of deaths. So with humans, for instance, population remain the same size of each pair of adults. You know, I know this makes it sound really nice and neat that everybody just has a pair, but just for the scenario, if each pair of adults produces exactly 2 offspring, and each of these offspring also reach adulthood and have 2 offsprings again. And in the real world, this doesn't happen. We either have more kids or less kids. People die along the way. Not everybody makes it to adulthood. So theoretically, it's 2. In reality, and with humans, 2.2, factoring in some people don't survive to adulthood. But if the adults in the population are not replaced by new births, if our population rate is below 2, then the population slowly sinks. That's just the basic math and simple how a population grows or shrinks. Now, how fast can a population grow? As a general rule, populations stay about the same from year to year. If we look at the population of Gainesville this year, last year, the year before, it doesn't change drastically. Just simply because from year to year, various factors kill some organisms before they can reproduce. We talk about deer in the woods. Some of them die to natural causes or other factors, they run in front of a car or what have you. And these factors help to control the size of the population, and they also kind of control how a population evolves. Since not every member makes it to adulthood to reproduce, this is where natural selection kicks in. As nature selects the organisms that are able to reproduce for whatever the reason may be, their ability to survive, a population can change, evolve over time. Now, a species' biotic potential is the fastest rate at which its populations can grow. So I could calculate how fast the people in Gainesville could grow if everything was perfect. We had all the food we need, we had all the space we need, with all this stuff. Or I could calculate how many mice would grow in a year if I started with 2, as long as they had plenty of space, plenty of food, and there weren't any predators. That's something's biotic potential. Now, this biotic potential is also limited by something's reproductive potential. How many offsprings can they have? For instance, humans, as a general rule, tend to give birth 1 at a time. Mice, as a general rule, tend to give birth to about 10 at a time. So there's a big difference. Sea turtles tend to give birth to like 200 at a time. Depends on the species, but this is reproductive potential if everything made it to adulthood. Now, some species have much higher reproductive potential than others. Charles Darwin, many years ago, calculated that it would take about 750 years for a pair of elephant to produce 19 million descendants. You know, they give birth, tracking the whole thing. But a pair of bacteria, they could do this in a matter of days or weeks. So get 19 million, elephants 750 years, bacteria at the most weeks. Huge difference in biotic potential, and a lot of it because of reproductive potential. Now, reproductive potential increases when individuals produce more offspring at a time, when they produce more often, and when they reproduce at earlier in life. So obviously, something that has 10 babies every time makes a big deal. Something that has 10 babies twice a year will have more than something that could have 10 babies once a year, and something that can start earlier in life. Now, of these 3, reproducing earlier in life has the greatest effect on reproductive potential. I take humans for instance. Now right now in America, the average age of women starting a family is 29. Let's just make it 30 for the math to be. So you're 30, you have a child. When you're 60, you have a grandchild. And then when you're 90, you have a great-grandchild. Make it be 90. Now let's take it if you started earlier, if say 15. I'm not saying what's good or right, but just it's about when females can begin. So they start at 15. 15, you have your child. By 30, you're a grandmother. By 45, you're a great-grandmother. By 60, great-great. By 75, great-great, and then up to 90. So it's 6 generations instead of 3. So this is why starting earlier tends to make the biggest difference. Now small organisms like bacteria or insects tend to have very short generation times, and they can begin reproducing when they're a matter of hours or just a few days old. Bacteria definitely in the hours range. Some insects, most insects, we're talking days. So obviously their populations can grow outrageously quickly. In contrast, however, large organisms like humans, whales, elephants, a lot of our large mammals fit this category, don't become sexually mature until many years later. Like in humans, somewhere in that 13 to 15 range. In elephants, it can be in the same, if even a little longer. So they have much lower reproductive potential than, say, insects or bacteria. Not that any of that is really shocking. This reproductive potential takes us to exponential growth. Now, exponential growth as a vocabulary term is just a logarithmic growth, where the numbers increase by a certain factor each successive time period. What does that mean? It just goes up, 2, 4, 6, 8, 2, 4, 8, 16, 32, 64. This is classic exponential growth. Exponential growth in nature only occurs when there are no limiting factors, if you will. The population has to have plenty of food, plenty of space, no or incredibly low amounts of competition, and no predators. If all that is there, then a population can grow exponentially. We saw this when we tested our bacteria. We put the bacteria on the growth plates, and within 3 days we could see colony growth. By 7 days it had practically taken over our petri dish. But out on our desk, our phone, where we were getting samples, we didn't see colonies of bacteria. So we were putting them in the environment. Once again, they had space, they had food, they had no competition, and they were able to grow exponentially. Now, when we get exponential growth, we get what we call a J curve. So this is our J curve. Large numbers of individuals are added each successive time period. So in this case, in a matter of months, we go from 0 all the way up to 800,000. This would be tracking something like bacterial growth in a petri dish. But we have limits. So we will see exponential growth, and we get what we call this classic J curve. But natural conditions are neither ideal nor constant. It might be ideal for a while, but it's not going to stay that way forever. And because of this, populations can't grow forever. If they could, be overrun with ants or grasshoppers or whatever the case may be. But eventually, the resources get used up, the environment changes, the deaths increase, births decrease, something. When we can't have as many births, and we start having more deaths. And under the forces of natural selection, only some members of any population are going to survive, especially when we start getting more competition, we start reaching this carrying capacity. And this is what really drives evolution. Once we have competition, then it's only the survival of the fittest. Those best capable, best able to reproduce do. Now, our human population, since about the 1800s, have been tracking on this J-shaped curve. We're yet to reach our carrying capacity. We're not exactly sure what it is because different things can help allow to continue to grow, cultural changes as well as technological changes. But anyway, eventually, every population reaches a carrying capacity. This is the largest population that an environment can support indefinitely. Now, we might say at a given time, right now, carrying capacity could be here, later it could be here, later it could be there. But when we talk about carrying capacity, we're talking about that can remain indefinitely. Our children's children would expect to see the same type of population. Now, a population can increase beyond this number, but it can't stay there. Things will supersede, they will go beyond their carrying capacity, but eventually it'll fall because of the limits, the limiting factors. And since the environment changes, ecosystems changing, carrying capacity can be really difficult to predict or calculate exactly. What we tend to do is look at average population, or we look at a population that's crashed. Okay, they definitely exceeded it, and we see what happens. What that looks like is this. So we see a population, let's say this could be deer, if you will, and the population has everything it needs, and it grows and it reproduces incredibly rapidly. It overshoots its carrying capacity, pretty common, because you still have. Now all of a sudden there's not enough food, and people are looking for food, there's not enough, and the ones that can't find it die. And we dip below the carrying capacity. Well, now there's enough food for everybody again, and we rise above it, and down and up. And we get what we call an S-shaped curve. That's this wiggly line. If you turn your head sideways, kind of looks like an S. So we have a J-shaped curve, and eventually they give way to S-shaped curves. Now it shows this idea that a population can crash. If it succeeds that carrying capacity by too much, then there's no food, the environment degrades, and the entire population can crash way back down to just a few organisms. Sort of rare, but we have lots of examples of it actually happening. And it's a concern in certain populations. Now, when we talk resource limits, any species is going to reach this carrying capacity when it consumes any particular resource at the same rate as the ecosystem is producing it. Like food is being grown. Food's growing up, and things are coming around and eating it. And if things here are eating all the food that's there, that's your carrying capacity. And that natural resource is called a limiting resource or a limiting factor. And the supply of the most severely limiting resource determines the carrying capacity. If the most severe limiting resource is space, well, then that's what we go from, food or water. The big three for terrestrial organisms are that. It is food, space, and water. A lot of times we're talking about space, we're really talking about density dependent. How dense can it be with organisms? But those are our big three. And whichever one is in the least supply, that will determine the carrying capacity. We also have competition, obviously within a population. Competition is the most common between other organisms. We all want this thing, but competition also occurs obviously within a same population. We all want the same type of food. Since we're the same species, same place, same time, we're all trying to get the same things that we all need. So we're using the same resources in the same way, and we'll compete with each other. Now, a lot of times members of a species may compete indirectly as well, either for social dominance or for territory. So competition within a population is just part of the pressures within natural selection. Once again, natural selection always comes down to reproduction. That thing which is most capable of adapting to its environment, living longer, tends to reproduce more often, passing on those genes. Now, territories, wherever something lives, is an area that tends to be defended by one or more individuals against some others. The deer here protect theirs from other coming in. This is very classic in our predators, carnivores, etc. They tend to mark and defend their territory because they can't have very many other large predators in the same area. Now, territory is not a value only for the space, but also for the shelter, the food, and for the breeding that it can contain. So these things are defended fiercely. And many organisms actually spend a very large amount of time and energy competing with the same members for these things, for mates, food, and home for their families. There's competition within the same population for these things, and a lot of energy winds up getting expended on those. Now we look at two different types of population regulation. Population size can be limited in many ways that may or may not depend on the density of the population. So we're going to talk about density dependent and density independent factors in something dying. So when we talk about organisms are going to die, some things are what we refer to as being density dependent, others density independent. Density dependent. When a cause of death in a population is density dependent, this means we're going to have deaths occur more quickly in a crowded population than in a sparse population. So this means it gets population regulation. Because there are so many organs close together, the likelihood of many of them dying is higher. Now, several things will tend to lend to this. Limited resource. We have a whole bunch of organisms here and limited resources. A lot of them are going to wind up dying because there's so many there, density dependent. Predation. A predator comes into an area where there's a whole bunch of deer. More of them are going to wind up getting killed because they're in such a tight space. Disease is also classic amongst this. One organism gets sick and it can spread to everybody in it if they're very densely packed. We know this, we look even in human history. Bubonic plague, Spanish flu, etc. come from this density dependence. So sickness tends to be one, but limited resources, predation, and disease, kind of big ones that we talk about for density dependent. The other side of that is density independent. Now there are some things, certain proportions of populations are gonna die no matter what, right? Just because I keep myself away from the masses and I'm somewhere where there's good food, etc., there are things that will control a population that are density independent. In other words, these types of situations affect all populations in a very general or a uniform way. Severe weather, acts of God, if you will. A hurricane comes through. It doesn't matter if I'm really close to everybody or I'm spread out. That hurricane coming through is devastating for anybody, whether you're close together or not. So very severe weather, natural disasters, and I usually throw in there time. Old age tends to take people out. Doesn't matter if you're in a density dependent or density independent, eventually organisms die. And make sure you can distinguish between this idea of cause of death because of density independent or the likelihood, and cause of death likelihood because of density independent. That wraps us up for section 1. Join me next time when we dive into another part.